Okay, I guess we can start. Good afternoon, everybody. Welcome to today's session. Once again, my name is Ridwan Salahuddin. I'm glad to be taking you through this discussion today. So if you're just joining us for the first time, this is an initiative by DataFin, a short for Data for All initiative. So our goal is to assist with building capacity in the field of data science and artificial intelligence. We mainly offer free courses and mentorship to interested persons, and we are open to people that are quite interested in learning about data science and artificial intelligence joining our sessions. So thank you for having me. So today is the day 8. Yes, so this is the 8th day, is the day 8 of the program Data Science Fundamentals. So we started some 4 weekends ago. We've been having it on Saturdays and Sundays, and this is the 8th session we'll be having. So far we've taken courses from Introduction to Data Science to NumPy, to Pandas, to Matplotlib, and yesterday's session was about types of machine learning algorithms, which was delivered by one of our partners, one of the mentors of Data for All initiative, the person of Bumi Balogun. Okay, so today we'll be discussing understanding learning algorithms, and the case study is logistic regression. Logistic regression. So although it's logistic regression, you can't talk about logistic regression without touching on linear regression. So we're going to cover all of that today. And as much as possible, you will get to understand some of the things that happen behind the hood in these algorithms. So we're not just taking you through how to implement it. We're trying to make you understand why different parts of it is as it is or function as it does. So without further ado, so this is the outline of today's discussion. So we'll start with definition of regression. Then we'll clarify the concept of prediction as just an approximation. Then we'll contrast linear and logistic regression algorithms. Then we'll proceed to discuss the mathematical representation of linear regression. Then we'll discuss the concept of cost function and what it means and how it is implemented. Then we will also discuss sigmoid function. So we'll also understand, we will also get to, for the first time in this program, implement a predictive, or we will build a model. I think it's more apt to put it that way. So we're going to build a linear regression model and a logistic regression model. All right. So let's start with the definition of regression. So what is regression? So if you do a Google search, you will find most definitions that center around what I have here. It is a measure of relationship between a dependent variable and one or more independent variable. So what does that really mean? Okay, so to make that a little more intuitive, so a dependent variable, just as it implies, is a variable whose value depends on other variables. So if I want to know if it's going to rain tomorrow. So to know if it's going to rain tomorrow is a dependent variable. What is it depending on? It's dependent on the weather conditions today and the forecast from today. So, and the forecasts from today are also dependent on, or let me just say, to rain tomorrow is dependent on the weather conditions as observed or as recorded today, and the climate condition and all that, and a host of other things. Okay, somebody is asking a question. Just for a moment, let me read it out. If somebody said the audio is breaking, I guess that's my internet connection. Okay, so let me know once it is clear. I'll continue explaining what regression is, and only go forward on when I get a signal that the connection is okay. Okay, so regression, as I was saying, is a measure of relationship between a dependent variable and an independent variable. So a dependent variable, we said, is a variable whose value depends on other variable or other constraints. So to know if it is going to rain tomorrow, we have to take the measurement of the weather today, the atmospheric pressure, and a host of other things that can potentially give us a hint as to whether or not it will rain tomorrow. So, and how about the independent variables? So all these variables that are going to tell you whether or not it's going to rain tomorrow, they are the independent, because they don't depend on anything. They happen and they just happen. So they don't really depend on anything to have their own value. So although that is in the context of what of the dependent variable. So in the context of the dependent variable, they are independent. In other contexts, they may be dependent. But so let's just limit it to the context of the dependent variable, which is to rain tomorrow or not. So it's dependent on the weather conditions as measured today, the atmospheric pressure, the humidity, the sunlight, and a host of other signals that can be measured. So clarifying the concept, so clarifying the concept of prediction as just an approximation. Okay, so you must have heard a lot of times when there will be projection that by the year 2035, this social country's population would have reached, say for instance, Nigeria's population would have been at 300 million. So you get such projections. So such projections are not just based on just self-thought or just personal feeling. It's usually based on some empirical methods. Usually a scientific approach to it. So it's based on historical record and trends, and they use it to make such projections. However, I am quite sure most of us have witnessed over time projections that were made in the past of the present time we're in, that were either off by a positive value or a negative value. So what I mean by that is they were either more than or less than the projected amount or value. So say for instance, it could be projected that by the month of September, or let me make use of the current time. So say nobody thought about COVID coming up in this year. So it could have been projected that say Nigeria's currency value to dollar would be at say 350 per dollar. So that's a projection. But then came this time and we have the dollar rising up to 400. So obviously when somebody makes a prediction, it does not mean that that value predicted is absolutely going to be. because the approach used to do that even does not really support that happening. So, however, it is just an approximation that ideally, given that we don't have such external condition as COVID that came up, so such projection, even if it is off, would not be by a wide margin. So, like I said, assuming we don't have the situation of COVID, if the projection was for Naira to be at 350 in this month, yeah, it's quite likely that it will not be at 350. In fact, there's a very high likelihood that it will be at 350 because this is a continuous value prediction. I mean, imagine there's a wide range of, in fact, unlimited range of values that the prediction can take. It could have been 350.01, it could have been 350.05, it could have been 351, it could have been 349.002. And so if you look at this value, it is actually limitless. The number of values or the number of fixed values you can take is limitless. So this is what continuous values are. What describes, what is known as continuous value. So values that are not discrete. Unlike, say, you're predicting 350, 351, and all that. So, so if such predictions were made, so there's a good chance that Naira may not be at 350 that was predicted, but it could be at 349.5 or 348 or 347 or 353. But you'll agree that the difference should not be much for a good prediction. So that is to tell you that predictions of continuous values especially are just approximations of those values at that time. So we will see when we illustrate it further as we go on. We will understand better what I mean by that. Okay, so as I proceed, if you have questions, I recommend that you type them in the chat box, or if you wish to, indicate by raising your hand, and I'll ask you to say your question. Okay, so what is contrasting linear and logistic regression is what we're discussing now. So what is a linear regression? What is a logistic regression? How are they similar? And at what point does the similarity start to diverge? So to answer that, let's go through the definition I have here. Logistic regression tries to provide an approximate output prediction given a set of independent input variables. So given a set of independent input variables, say what the temperature of tomorrow will be. So linear regression tries to, I beg your pardon. Given a set of independent variables, independent variable in this case, let's assume we are limiting it to just one independent variable. So the temperature of today, knowing the temperature of today, you want to be able to predict what the temperature tomorrow will be. So the temperature today is independent. It doesn't depend on, it has happened and the value is there. So it's independent variable. So given this independent variable, if you have to provide an approximate prediction of what tomorrow's temperature will be, so what you're doing is linear regression. So I hope my explanation is intuitive. However, if it is not, I still have further explanation and data to illustrate it here. So it is said to be used for continuous outputs. Like I explained, continuous outputs are outputs that are not discrete. So the temperature can take any value from probably minus infinity to plus infinity, hypothetically. So it can take -3, can take plus 35.7, plus it can take 42.69. It can take so many values. So this continuous prediction is known as, or this type of values are called continuous values. Now, for example, so this data we have here, like I said earlier, we're trying to predict what tomorrow's temperature will be based on the value from the average daily temperature. So today's temperature, you want to know what tomorrow's temperature is. So this is a classical example of a linear regression. I hope this explains it well. I hope everybody understands what linear regression is at this point. I just need one person to answer. Most likely I want somebody who doesn't understand to say, no, I don't understand.
I don't understand yet, although I joined late.
Okay, so I'll take it again. So linear regression, based on the definition I have here, tries to provide an approximate output prediction. Or let me say, tries to provide an approximate prediction, or tries to provide a prediction given a set of independent input variables. This is just the definition of maybe prediction. For you to make prediction, there has to be some values that you're predicting on, that are using to predict, right? So given that you have some independent values, and I've described what independent variables are variables whose values don't depend on anything. They happen. Probably you just measure them, and if you just measure it, then it doesn't depend on anything. But tomorrow's temperature, we want to be able to predict it. So it depends on the temperature today. So don't try to take this illustration too scientific, because I'm just giving this illustration. There may not be a significant correlation between today's temperature and tomorrow's temperature to make such predictions. But let's assume it is possible in this situation. So now, given that you have temperatures measured a day before, you want to predict the next day's temperature. So that is an example of regression. So, but what makes it regression is the fact that the value you're predicting is not a yes or no, or is not a cat, dog, and sheep prediction, or is not a high, low prediction, or is not a will it buy or not buy prediction, or is not a maybe variety of dogs, say this type of dog, or this type. You're not trying to break it into a finite set of outputs. Let me just use that to concisely describe it. So what you are having is not finite set of outputs. Rather, it is a continuous set. It can be 0. Tomorrow's temperature can be 0. It can be 50. It can be 70. It can be 65. It can be 42. It can be 31.5. It can be minus 0, minus 2.9. So this type of outputs are what is what makes this type of prediction regression. Does this answer your question, or does it make it clearer to you?
Yes, thank you very much.
All right. So looking at the table I have here, it also gives the illustration for that. So what we have here is what we are predicting, the next day temperature. And you see it can take any value. You don't have a specified number of values it can take. So that is what makes it regression. Linear regression in this case especially, or let me say generally regression though. So, but regression can now be adapted to classify, or let me say to group things into, okay, will it rain or will it not rain, for instance? Or will tomorrow's temperature be high or low, for instance? Or tomorrow, or will it buy the good or not buy? So regression predictions can be adapted to logistic regression. So what does logistic regression mean? Logistic here is what differentiates linear. Fine, I think that's quite obvious from the names even. But what logistic means is you're trying to estimate the probability of one event happening over the other event, or one of the output being one thing instead of another thing. So where you have a finite number of outputs. So in this example, let's assume you're trying to say, will it rain tomorrow or not? So you have two options, rain or no rain. Okay, or you have a tweet, somebody makes a tweet, and you want to be able to say, okay, this tweet, is it a positive tweet, or is it a neutral tweet, or is it a negative? So let's define our positive, assuming that a positive tweet is a tweet that is praising somebody or praising a situation or praising something, or a neutral tweet is just a tweet that just maybe passes an information or just says something, and a negative tweet is a critical tweet. However, however way it appears. Let's just take that. So you have three outcomes here, but they are finite. It's not unlimited. It's not unlike the case of the temperature of tomorrow that was illustrated earlier. So where you have finite set of outputs, that is called logistic regression. So it can be just binary when it is just two, or it can be multi output, or I don't really have the word for it now. So it can have many number of outputs. It can be 3, can be 5, can be 100, can be theoretically, it can be 1,000. Can be 1,000. At least I've worked on a model that has 137 outputs, where you have to classify into up to 137 outputs. So, but as long as it is finite, then what you have is logistic regression. As long as the output you're working on is finite, is a finite set, is logistic regression. Is that clear to everybody, please?
Yes.
Is there anybody who doesn't understand what logistic regression is or how it's different from linear regression? Okay, so I assume nobody. So the table I have here is just is the same record from above, the same table from linear regression. But here now, we've set a threshold that any temperature above 25 degrees is high and any temperature below it is low. So we want to simply predict whether tomorrow's temperature will be high or low. So here, we're not really after precision, right? You don't have to try to be as close to tomorrow's temperature as possible. If tomorrow's temperature is going to be 35, what we need to know is whether it's going to be high or low. Even if your regression gives 30, as long as it is high, then it is correct. So if tomorrow's temperature were to be low, so even if the actual temperature is going to be 5 degrees, but your model predicts 24, it is still correct, although the confidence level is low because it's quite far from the actual, but it still gets it correctly because it still predicts that it is low. So this is what logistic regression is about. Okay, somebody has in the chat a word categorical. I'm not quite sure I understand what the person is trying to say. If you don't mind, you can speak up or you can still type further explanations. I understand what you're trying to say. Okay, so I'll go on. You can type it in or you indicate that you want to talk then. Okay, so I hope this explains what logistic regression is. Now, mathematical representation of linear regression. So most of these models, they're actually built on mathematical foundation. If you're, however, not the mathematics kind of person or the person that is scared by mathematics, you need not worry. So this will just be taking you don't really have to understand it deeply to use it. So that's what I want to say. So although if you want to go really deep into machine learning, artificial intelligence, you will eventually have to learn the mathematics behind it. However, for now, you can just try to follow up if you know you are not quite strong. So don't get discouraged. That's the message I'm trying to pass. Don't get discouraged about this. It's quite straightforward. It's quite simple though, and I will try to explain it as intuitively as I can. So mathematical representation of linear regression. So linear here, let's take notes, not logistic regression. We'll get to logistic as well. So the above illustration, the illustration above can be represented with a linear equation as shown below. Okay, so you know the illustration we have in these tables here just makes use of one variable as the independent variable, right? So in real life, or most times, you will be having more than one. But if you understand how it works with one, it's the method or the understanding from there can be translated to multiple multivariable prediction as well. Okay, so here we have y equal to wx plus c. So I use w subscript 1, x subscript 1 to indicate that this can be more than 1. So x here is the independent variable or the input value. I think I should rather use independent variable. I put input value here. Input value values. Independent variable. Okay, so x is the independent variable, the one that is used to predict outcome. All right, so we have w here, which is just a constant number. I mean, if you are used to, from secondary school, if you learned the equation of a straight line, I mean, even if you did sciences, you'd have learned the equation of a straight line. If you did commercial, you'd have learned the equation of a straight line as well. It's only if you did arts that you may not have come across the equation of a straight line. So this is a classical equation of a straight line. Y equal to, it's usually mx plus c. So, but in machine learning, it's usually, the m is usually substituted with w. So w implying weight. So weight. Okay, I forgot to add it here as well. So weight. Now, what does this weight do? So in a, okay, I don't have a linear, I'm going to open equation of a straight line here. So I can use it to explain the concepts of slope, just briefly. You don't really need to pay too much attention. Okay, so we have this. This is a straight line. The straight line has slope m, and it has intersect b. So the intersect b is the y-intercept, rather, not intersect. Intercept. Now, m is the gradient. So gradient is change in y divided by change in x. So this line can be described using just these two values, m and b. So if I know what m and b are, I can produce this line exactly as it is once I'm given the values of m and b. So having these two values can describe a straight line. Now, that's the message I wanted to pass. So let's come back to what we have here. Now, y is our output, the one we're trying to predict. So 10 minutes from now, we will break and resume immediately. 10 minutes from now, we use the same link to reconnect. All right, so now, y is the output you're trying to predict. X is the independent variable. So w and c are the values that describe the line that is going to make this prediction possible. So the line is now generalized using this equation. So what this tells us is, once we know what our W and C is, we already have this model built. I don't know if it is clear. Once we know what our W is and what our C is, so we'll only need to know what X is today, and we'll tell you what the weather is tomorrow. We know what X is yesterday, we'll tell you what the temperature is going to be tomorrow. I mean today. So let me just add a cell. Sorry. Let me add a cell below. So let's assume our W is equal to 5. Our C is equal to 2. Now we can say, okay, what is the value of Y when X is so, right? Because X is independent, we're going to have the value of X at every given time. So when X is this so value, what is Y? So our Y is going to be what? W times our X, right? So X can be anything. So let's say in this example, our X is 9 plus our C is 2, right? So let's print our Y. Sorry. All right, so we have 47. So here, even if our X, remember this is our X here. So even if our X changes, we don't need to change anything. So once we have our W, did I put 2 here? I was supposed to put C, sorry. So once we have our W, we know that we have our W and our C, we know that we have built this model. So that is the message I'm trying to get across. So the essence of this equation is to get what the value of W and C is. And if there are more independent variables than shown here, so we're going to have as many values of W as there are independent variables. So if there are 2, we're going to have W1, W2 plus C. If there are 3, W1, 2, 3 plus C, and so on. All right. So now we have an illustration here. I'm going to delete this. I have an illustration here that I created. I have this data here, this data point here. So let me print out the values of X and Y. So we have X and Y. So let's take X to be the temperature today and Y to be the temperature tomorrow, right? So we're trying to predict tomorrow from today. So we have something like this. So we know when we discussed plots, creating plots, we said plots like scatter plots can easily be used to show correlation between different data points. So we're going to plot a scatter plot here with X as independent variable and Y as a dependent variable. So after plotting that, we will try to fit in or create our predictor line. You know, we said this equation of straight line gives us a straight line that gives you that approximates the data we have. So we're going to try to generate that here manually, like the same thing computer does, but we're doing it manually here until we get something that works. So first, I'll say I import my matplotlib, and I'll just create the plot of the data point. So you can see it all scattered around. We don't know we're discussing linear regression, right? So if I were to say, okay, remember these are x-axis. So if I were to say, when the temperature is 25, what's today, right? When the temperature is 25 today, what is going to be the temperature tomorrow? So as it is now, we can't really tell because there is no line to map this our x-axis, to this our y-axis. There's nothing. I mean, what if I want to plot this 25 points, against what value of y will I plot it? Will I put it here, or will I put it here, or will I put it here? Like, I can put it anywhere along this straight line, from this straight vertical line at this 25 points. I can put it anywhere along this vertical line. However, once we add our predictor line, so assuming that this predictor line that I'm adding was gotten using this equation. Okay, so typically, the first time the algorithm starts to learn, so I'm going to put random, I'm going to change this value to something more random, 20, 450. All right, so let me run it again. So I can see where the line is. This is obviously wrong. So when such happens, the algorithm is going to, as we'll discuss later, estimate what the error is here using the cost function. So it's going to estimate what the error is here. And because the error is very large and this thing is off, like it's way off, so the algorithm is going to tell it that, okay, you're off, but you need to come up a little bit. So because we are not really running it, so I'm just going to try to change values around until we get close. So this is my y. Let me this is my x. This is my y. All right. So what we need is this corresponding value of y at this 50 to be bigger. So when y is 50, when x is 50, sorry, we want y to be bigger. So this line here can go up. So when y is 50, let me make this, say, let's take it up to, say, 52 first. Oh, I beg your pardon. Sorry. Okay. So we can see that it has lifted the line up, but it has also gone above all the data points here. This does not look like the best approximation for this data. I mean, if you're told to draw the best line that approximates this data point, this does not look like it. So what can we do again? Okay, this 50 seems to be extreme. What if we reduce it to, say, 45? Okay, this looks better. What if this 12 here, let's see, this 12 here, what if it becomes, say, 13? Let's see. Yeah, it's also better. Okay, what if this 45 still comes down to, say, 43? Yeah, still better. So, I mean, this looks very close to the best we can get here, right? So we should stop here. I think our time is up, and resume back immediately. Yeah. Welcome back. All right, so welcome back. Now, we were explaining how to get the line of best fit. So this is typically what the algorithm does. You see, the way I'm changing these values manually, so that's what the algorithm is doing. Basically, what I have here, this value describes the slope of this line. What I have here describes the slope of this line. So you can think of this as the M. All right. So we seem to have the best line here. We can still touch it around a little bit, maybe by making this 14. Yeah, this still looks better, I guess. So you know the goal is if you to measure the error, because what this line is saying is, you see this data point here, according to this line, this data point here should instead be on this line here. This data point here should instead be on this line here. This data point here should instead be on this line. But you'll agree with me that the line is wrong. The points plotted are the actuals. So that tells you that this line is still having some residual errors in it. So the line has some errors. So that is inevitable. That is why it is called an approximator. So it's just trying to provide a universal approximation. So not an approximation that works well for some data points and not well for others. So it tries to get, on average, the best approximation. So if you were to measure this error plus this error plus this error, that we can call as negative errors, and this error here and this error here that we can refer to as the positive errors, they should sum to 0. So that will tell us that this is the best approximation that we can get. So this is what is called convergence in machine learning. Any question at this point? Is there anybody that is confused at this point? If there's anybody that's confused, you can stop us before we move ahead, because we're learning a lot of things today. I don't want us to wait till the end before we start saying, okay, I didn't understand this. So let's try to get everybody to follow along. Okay, so I'll assume everybody understands what we're discussing so far. Now here, concept of cost function. So, you know, I made reference to errors here, right? So the first approximation we got was very, very bad. And the error, of course, if you were to measure that error, is going to be so large. So such error now needs to be estimated. Okay, how badly is this model, is this this approximation, how bad is it? So once you're able to get how bad it is, you can now decide to move in a direction that will minimize that error. And that is why we knew where to move. So we can see it here, but we need to have a way to make the computer see what we can see. You know, because I plotted this out, it was easy for us to see, to visualize it, right? And we could tell where to touch to make it better. However, the computer needs a way to see this same thing we can see. And that is where the cost function comes. So this cost function, so don't be confused when you read online or maybe attend other courses or find anywhere else where it is referred to as loss function or where it's referred to as the objective function. So the concept of cost function or loss function or objective function is to estimate how badly a model is performing and to make correction to that model. So that is what the cost function does. I take it again. The cost function is used to ask the model, how badly are you performing? And based on how badly we know it's performing, or based on how badly the model is performing, it makes changes that are meant to minimize this cost function. So this tells us that in any machine learning algorithm you're building, in any predictive model you're building, your goal is to minimize the cost function. So let this resonate with you. The goal of every machine learning model is to minimize the cost function. So cost function, okay, let's see, what's the intuition behind the name cost? So take, for instance, you're at home and you notice that there is an exposed electric cable around. So you're living there, you have your siblings there, and you have other relatives. So you could choose to ignore it. That, I mean, okay, I know I'm not going to get hurt after all. However, what if somebody else close to you gets hurt from it? There's going to be a cost to it. So the goal is to minimize that cost. So when you see it, you now start thinking, okay, how can I minimize this cost? One of the options is, okay, if you know your way around, you can look for a tape and close the exposed cable. So it minimizes the risk. So by so doing, you have minimized the cost of that, the cost that can result from that cable. Okay, so let's say you're also going to, say you want to make an investment, right? So most of the times, your goal is to minimize the costs. You're setting up a business, and every action you're taking is to ensure that you don't spend so much. So you are trying to minimize your cost at all times. So I hope that intuition, you're able to translate it to machine learning, that the cost, think of it as a consequence, right? Consequence here is the error, right? So the consequence, given the situation you're in, what consequence can result from it? So you want to say, even if there's going to be consequence, let it be minimal. Let it be minimal. So that's what you want. So you want to minimize the cost. Now, since models trains by trying to find the line of best fit, remember we're discussing linear regression and logistic regression. So I highlighted that because this assertion may not be the same when we're discussing about other algorithms. So since the model trains by trying to find the line of best fit, it is essential that we have a way of measuring how well the model is performing. So this is achieved by defining the cost function. So the cost function will serve to nudge the model one way or the other, depending on how well it is performing or how badly it is performing. Now, common cost functions. So these cost functions are of different types, and different cost functions are suitable for different tasks. So where you have a regression task, you will want to consider mean absolute error or mean squared error. So either of these two are suitable in when you're working on regression model. So what is mean absolute error? I don't have the definition here, but think of it as, so you have an actual value. You're trying to predict what tomorrow's weather is. Tomorrow's temperature. So you predicted that tomorrow's temperature is going to be 35. So when tomorrow's temperature was actually measured, that's after, of course, when tomorrow comes around, yeah? So when it is measured, it is found out, it's found out that the temperature is actually 32. So there's an error there. So what is your error? The error is the actual minus the predicted. The actual is 32. The predicted is 35. So that's what you found out. So your error is 32 minus 35. So this difference is your error, but it's not the mean, it's not the absolute error. So absolute error is non-negative. So that's what absolute means. I mean, if you've heard the word absolute value, so absolute value is used to refer to non-negative value. So if you take absolute value of any value, it's going to return negative. So absolute value of -5, for instance, let me illustrate that using so Python has the function absolute. So minus 6, and we get 6. So in this example, we say 35 is the measurement, 32 is the actual temperature, and 35 was the predicted. So the error is 3. 32 minus 35 is actually minus 3, but because we're measuring the absolute, so it is 3. Now, not just absolute, this is the mean. So because we'll be having many here, right? So here we have 5 data points, right? But this one has its own error, small. This one has its own, small. This also has its own, small. This one's have is a little big, right? So you take this error, and let's assume this one is 0.1, 0.1, 0.1, right? They're actually less than the actual. I mean, yeah, the actual is less than the predicted, right? So minus 0.1, minus 0.1, minus 0.1. So that gives us minus 0.3 together, right? So, but because we're taking the absolute, so instead of having minus 0.1, it's just going to be 0.1. So we have 0.1 in 3 places. Then here, let's assume these ones are 0.2. So these ones are not even negative because they are bigger than the actual. I mean, they are bigger than the predicted. So let's call this 0.1 and 0.2. So 0.1, 0.1, 0.1, that's 0.3, then 0.2, that's 0.5, then 0.2, that's 0.7. So let me write it out here. 0.1, remember we're using the absolutes, right? Plus 0.1, plus 0.1, plus 0.2, plus 0.2. So these are, I'm assuming I've taken the absolute value. That's why I don't have negative here. So when you sum these up, this gives us the total error. So we have to take the mean of it. So what do? We divide it by the number of values there. So we have 5. So this is our mean absolute error. So the other error function, so the other error function is mean squared error. So mean squared error, the difference is just that. So instead of leaving this as it is, we're going to square each of it. So this squared, 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 squared. And so instead of the value we had earlier, so this is what we're going to have as our error when we use mean squared error. So like each of the error has to be squared. That's just what mean squared error means or refers to. So the third is cross entropy. Cross entropy is used in classification. So we will be using it later today. So this class is likely going to extend beyond the projected 6 o'clock. I beg, I crave your, I seek for your permission to exceed that time. All right. So sigmoid function is the next thing we'll be discussing after discussing the cost functions. We said cost functions are used to estimate how well the model is performing. So sigmoid function, when we're discussing predicting tomorrow's weather from tomorrow's temperature from today's value, right? We said when we're making that as classification, we can set a threshold of 25 and say, okay, any value above 25 is high, any value below it is low. However, when you're training a machine learning algorithm, so because in that example, we had 25 as our reference point, what if we never were told what threshold makes high or low? It's quite possible that we're not told that, okay, what's the threshold for saying this is high and this is low? So this is where sigmoid function comes handy. So now, still, let's go back to that example. So assume that we're only giving the data set. Let me go to the data. So we're giving this data set without the prior knowledge of what the threshold is. So we can transform this to 0, the high to transform the high to 1, and the lows to 0, right? For instance. So, and our goal will be to predict 1 or 0 for high or low. We don't know what the threshold is. So we can't hard code it and say, okay, just predicts any value and when it is 25 or more, do this and when. So it's not possible to do that. So instead, we'll just say, okay, let this be 1, let this be 0. We create the model, and the result, or the regressed values, right? So the predicted value, which is going to be continuous, like we have expressed. So we are now going to threshold it using the sigmoid function here. So this is what sigmoid function does. So for any value that is predicted as outcome from your regression. So assuming we ran that model and it predicts, say, 10. Yeah, say it predicts 10. If you pass the value of 10 here, it's going to tell you, it's going to either give you a value below 0, below 0.5 or above 0.5. So this is 0 to 1, right? And this midpoint is 0.5. So for each value of x, so for instance, when x is 0, the corresponding value of y is 0.5. So if our model predicts or returns a continuous value of 0, automatically we get 0.5. However, if it returns anything above 0, then we get something above 0.5. If it returns anything below 0, then we get below 0.5. But our value cannot be less than 0, and it cannot be more than 1. It has to be between 0 and 1. So that is what sigmoid function does. It squishes your values to between 0 and 1. Any question at this point? Any question at this point? Okay, let's move on. So I'll still touch more on it. Now, because, okay, maybe using, I'll try to use another example now. I'll try to use another example so I can get that of temperature off our head. So let's assume you're trying to predict whether a customer will make purchase or not make purchase based on how much they have as account balance. Based on how much they have as account balance, whether he will make purchase or he will not make purchase. Now, it is always a good practice to, when we're talking about logistic regression, because obviously sigmoid function is used in logistic regression when we want to get a value of, say, 1 or 0, true or false, high or low, will happen or will not happen. So we're trying to bring somebody who will buy or not buy based on the account balance they have. Now, assuming after building the model just outputs values that range from minus infinity to plus infinity. But most likely, if the model has been trained well, most of the values will not be very far off. Most of the values would lie around 0. So most of the values will lie around 0. We'll discuss further on what is called scaling of your data before running model through it, but not today though. So once you have a value that is above 0 predicted, now okay, because this person has 10,000 in his account, the predicted, the regressed outcome is, say, 7.89. So that 7.89, when passed through this sigmoid function, is going to return a value around this place, which is somewhere in between 0.5 and 1. So maybe for another person that has just 500 naira in his account, the predicted regressed outcome, remember regression is predicting a continuous output. So the regressed outcome can be minus 3.89. So this minus 3.89, if you pass it in here, it's going to provide a value in between 0 and 0.5. So because 3.89 minus 3.89 can be somewhere around here, and when you map it here, you get somewhere around something along this place, around this place on the y-axis. Okay, so I have a little definition here, how to define a sigmoid function. So you can feel free to skip this. I'm not going to spend much time on it because you won't have to define it anyways. It's defined in the algorithm you're using. So I just wanted to do this so we can see how this is actually plotted. So I'm going to create some values here, some values of x, mp dot linspace. Sorry. Yeah, so mp dot linspace. So I'm going to create values between minus 20 and 20 and step it by 0.1. Now I'm going to plot this value against its sigmoid. So let me define the y. So the y is going to be sigmoid of x. So I'll just say plt dot plot. So plot x against y, and plt dot show. Excuse me. Oh, so I'm supposed to say a number of items. I want, let me say 50. Yeah. Yeah. Okay, so this seems too far off. So let me change it to between 10 and 10. Yes. So this looks closer to what we have here. What if I change between 7 and 7? Minus 7 and plus 7. All right, so this is what our sigmoid function is. So any value you pass in for x, let's do it here. So let's pass a single value into our sigmoid. So let's pass, for instance, let's pass minus 2 into our sigmoid function. We get 0.119. which if you look at it minus 2, if you map it to the y-axis, so we can see around 0.1 something. If you can see it, you trace it carefully. So if you change it to 2 as well, so 2 gives us 0.88. So this is our 2 here. If you trace it up, you get around 0.8 something. All right. So here, linear regression from sklearn library. So let's pay attention very well here because this week's assignment is going to be based off this part. So I've loaded, we'll see how to make predictions, create models using sklearn library. If you don't have it installed on your system already, on your Python interpreter, you'd run pip install sklearn to install it. So the documentation is here, and I recommend that you view the documentation for this linear regression. It's a linear regression documentation. So this link takes you there. So you open it and you try to at least look through it and see what you can understand. However, I'm going to explain it here. So I loaded in a toy data set here. I loaded in sklearn.linear model. So this sklearn package has a linear model module. This module has a function linear regression. And I'm loading in linear regression. This is just NumPy and Pandas here. So yeah, this boosting data. I loaded boosting data using this function that I imported here. So load boosting, I have the data here. Just ignore what don't pay too much attention here. This is basically reading the data that we're using for this prediction, for this model that we're trying to build. So we're building it together. I haven't done it. What I did here is just load the data. So let me say boosting DF so we can see what it looks like. So this is what the boosting DF looks like. So this boosting DF is a data of I beg your pardon. Okay, so I'm sorry, I didn't read the description. So we can get the description here. Excuse me, keys. All right, so I'm trying to get the description. All right, so this is the description. Let me print it nicely. So we can understand what the data set is about. Boosting house prices data set. Data set characteristics, number of instances. No, we don't need this. So it doesn't have any missing attributes. These are the column names. The data set was taken from Start Library, which is maintained by Carnegie Mellon. Okay, so this is the description. The boosting house, it is house price data of Harrison D and Robin Feld, DL, blah, 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 on demand for clean air. Okay. Well, was taken from, I'm actually trying to, so I just loaded the data set. I didn't try to understand, I didn't read about what the data set, I didn't read the description of the data set. So that's what I'm trying to get here, so we can at least get a context to what we are building. So it's actually a house price data, right? So it's house price data. Now let's go to the data and see. So this is the target output of that data. You can see it's nicely labeled target, and these are the columns there. These are the variables, so to say, the independent variables. So cream, ZN, if you want to get the description, you get it from here. Cream is per capita crime rate by town, and so on and so forth. All right, so I really don't have adequate understanding of the data sets to provide a better understanding. So, but if you look at the target is continuous. So it doesn't look like we have fixed number of outputs. It can take any value. So this is a very good regression data set. All right, so now let's see. We've been told that it doesn't have any non-values, but we can still try to see by calling info on it. So info tells us that 506, 506, everything has 506, and all of them are non-null. So no null value in it. So these are the typical things you'll do when you get your data. So you may want to also run describe, boosting df.describe method. So this will typically return some statistics for you, which I'm not going to pay too much attention to for now. So I'm going to upload this notebook I'm working on. It's currently uploaded on the GitHub link I sent. However, I'm still going to upload it again after this class, so we can have this updated version of it. All right, so we have seen that there's no null value, so we don't really need to handle our null values. and all the values we have are numerical, so we don't need to change our categorical variables. If we had it, we don't have it, so we don't need to worry about it. So all we need to do here is split our data into train and test. Train and test. So I've not really mentioned data splitting, but when you are building a model, you need a way to assess how well your model is performing. Okay, so should we run out of time, I crave your indulgence to still reconnect using the same meeting link. So should we run out of time? But I'll try to finish in time, but I think we have less than 10 minutes. All right, so I'm going to import, there's, in sklearn library, there is, I think, is it splits? I'm trying to remember the, I need a way to split. Sorry, I really can't remember the method for splitting. The train test split. All right. Model selection, yeah. So in the model selection module, from there, import train test split. So this is going to be used to split our data into train and test. But first, we need to isolate our targets from the main data we have. I'm going to, okay, df, boosting df. All right, so I'll isolate as y, I'll isolate our targets, boosting df targets, then I'll call x, the other part of it, boosting data frame excuse me. Okay, so beg your pardon. Targets. Okay. Okay, good. So we have our y and we have our x. Yeah, so we have our y and we have our x now. So now we need to split these two into train and test. So let's say train, okay, I'll move this to a new line. So let's say train x, right? Train y. Then test x, then test y. Now, we imported train test split, right? So train test split, we'll pass in our X, we'll pass in our Y, then we'll pass in the splits, how we want the splits to be done. So there's what you call test size or train size. So let's just pass in the test size argument. It should be sufficient. So test size, we want test size to be 20% of our data. So let's say 0.2. So this is effectively going to split our data for us. Now, we have imported logistic regression. So we have to instantiate the model first. Linear regression, I beg your pardon. So linear regression, this is telling, this is creating the object, the regression object, right? So we've created it here. Now, next is to fit this model on our data. So we have our train data here, train X and Y. Let's inspect our train X. So we can see train X is 404 rows, down from 500 and something rows. We can see our train Y too. Oh, sorry, I mixed this up. So it's supposed to be test. Yeah, test X. Yeah, so it's supposed to be this way here. All right, so these are our train Y, right? So train X, train Y. Then our test, we can as well check test X. So this is what our test X looks like, and our test Y too. These are the outputs. Remember, Y is the output that we already know. So what we'll do is, this test Y, we won't be using it to train the model at all, because it is the test data we want to use to see how well our model is performing. So we won't expose our model to it at all. So I'm going to just simply clean it up. So now let's fit the linear regression on our data. So it's simple. You just call linear regression dot fit, and you pass in the train X, right, and the train Y. So it is to train with X and Y, right? So this is the data, and these are the labels for the data. These are the outputs for the data points as seen here, right? So for this one now, the output is going to be the corresponding Y, or simply if I just call the Boston data. So for these values here, this is the output here. So we've isolated this output. All right. Now I'm going to call this fits on it. So this is the fitting stage. So I fitted my data on this logistic regression model, right? So next thing is to make prediction using this. So let's call the result of our prediction pred. Okay, I'm waiting for others to join before. So I guess we can move on now. So the next thing is to say, make predictions. So remember, we've trained on the trained data sets. So we'll be making prediction on the test data set now. So we've isolated the test data set, which is about 100. Let's see it again. Test X, about 102 rows. So with the 102 rows, we'll say LR.predict. So we'll be making the prediction using the test values, test X. So we'll store the result in pred. Okay, but let's stop and imagine for a moment. Why can't we simply make predictions? Why do we even have to split? So let's now I'll also try to answer it. So you're training a data and your computer has seen, I mean, this is just like, let's think of it as somebody wants to test how well you're performing, right? And it's only giving you the same set of questions that he has taught you with, that he has used to train you. So after using those questions to train you, he returns those same set of questions to test you. You'll agree with me that that's not going to be a good measure of your performance. However, if while training you, we have separated some data and some questions and not exposed them to you, so those ones will serve as good measure of your performance, and that's what you're trying to do here. So now we'll make our prediction and we can see the returned values here. So this I called predict, LR.predict. You can see with very few lines, we're already making our predictions. And here we have our predictions here. Now, how do we know how well our model is or has performed? So there's something called in sklearn. So we're going to import from sklearn.metrics, import score. Import score. Import accuracy score, I beg your pardon. Accuracy score. All right, so using this accuracy score now, we'll simply say, okay, our accuracy equals to accuracy score. Then what is our output? Pred is our prediction. What is the actual? Actual is test Y. So test Y is the actual, or is the actual value. So prediction are the predicted values. So let's print it. Accuracy. So let's oh, my bad. So what we're doing is linear regression. So in linear regression, like I said, how do we know how well our model is performing? We use cost functions like mean absolute error or mean squared error. So that's what we should be using here and not accuracy, because there's actually no way to really know our accuracy, since it's not a question of yes or no, fail or pass. So let's say let's use mean squared error. Yeah, mean squared error. Good. Mean squared error. All right, so the mean squared error we get is 21.84. So that's the mean squared error we get with this model. So what does this mean squared error mean? All right, so remember it is squared error. So that means whatever error it is, it has been squared. So if we were to take the square root of 21, we're going to get a number between 4 and 5. So let's say 4.5. So what this tells us is each of these predicted output here. So the confidence interval is plus or minus 4. So if I say the value here is 23.2, then it can be 23.2 plus 4.5 or 23.2 minus 4.5. So it can range between those two extremes. Any value between 27.7 and 19 or 18.7. So it's going to be valid. 18.7 is going to be valid. So that is what this mean squared error means. Now, there's something else we could have done to improve this model. And I said we will not dwell on it in this class, and we'll dwell on it more tomorrow. It is called scaling. So remember, these values here, some are like this NOx, most of the values are less than 1, whereas tax, most of the values are quite big. So if we scale this table, this data we have, it's going to make this all these values to range between 0 and 1, for instance, or maybe -1 and +1, and it's going to put them. It won't make one column so big that it can affect all the others. So we, okay, I think it's just best I illustrate that immediately. So I'm going to just add a new cell below and do it in one step. Import sklearn.preprocessing. So the module is called preprocessing module. From sklearn import. So let's use standard scalar. So you don't need to worry much. We've not discussed scaling data. So this is just to, well, if you see how I implement it, you can as well use it until you understand how well, what it really stands for. But it really works well, especially when you're working with logistic regression. All right. Standard scalar. Then SC. Let me see, SS is called to standard scalar. So I'm going to fit on ss.fit. I can just simply use fit transform. So we have to scale both the S and the So we'll basically retrain the model, fit the model by calling our would reinstantiate the linear regression again. So this is important because remember we've trained the model before. So if we don't do this again, it's going to continue training it with the already trained model here. So it's important that we reinstantiate it here before fitting it. So lr.fit on our train x, lr.predict on test x. So train x, train y. So these are pred. So accuracy is called to mean squared error, pred and test y. Accuracy. Okay. So, well, it doesn't seem to give a much, it doesn't even seem to be different from what we had before. Yeah, it's not different. So scaling does not really improve it much here. So we made use of standard scalar, and well, nothing much changed in the model's performance. Okay, so very quickly, I will also illustrate logistic regression. So this basically how logistic regression as well works. You can see how the model started out randomly, and here it's trying to optimize to separate the red parts from the blue parts. So this is like you have two categories and you're trying to separate them. All right, so until it has achieved the best separation, it's cool. So let's see here. We do same thing as we did above. Although here we're using the iris data set. So we load in the data set. I did some transformations here. So here we can see we have sepal length. So this iris data set is data, we've seen it before in one of the previous classes. It's data set about some flowers, Setosa, Virginica, and Versicolor. So these flowers, based on, they want us to predict or to classify each record into whether it is Setosa, Versicolor, or Virginica, based on the sepal length. Sepal is one of the parts of a flower. So sepal length, sepal width, and the petal length and the petal width. So let's see. So like we did above, we isolate our Y, that's the target. So these two here are actually the same thing. This is the numerical form of it. This Setosa is mapped to 0, Virginica is mapped to 2, and Versicolor is mapped to 3. So this is actually a 3-pronged classification and not binary. Okay, so let's see. So we'll say iris DF target, then our X, so X is equal to iris DF. So let's drop target and target names. Axis 1. So here we're going to still split into train X, tests X, train Y, test Y. So train test split X, comma Y, comma test size test size 0.25. Anywhere between 0.1 and 0.3 is the typical size that's used. So we've split the data. Now we need to import logistic regression. So from sklearn.model selection, from linear, still linear model, import logistic regression. So let's instantiate the model. We can call it, and it doesn't have to be LR, so I'll call it model here. Logistic regression. So we can just call it just to see. So that's our model. So now we need to fit the model to our data. Fit the model on the trained data. So say model.fit on train X, train Y. So now we make prediction. So we fitted make prediction. So we make prediction on the test data. So let's say our prediction is model.predict test X. So we are passing in just test X in order to make prediction. We don't want to give it expo by passing in text Y, although it doesn't accept it anyway. All right. So predicts, it's missing C. All right, so prediction made. Let's inspect our prediction. So we can see 1, 2, 1, 0, 1, 2, 0, 0, 1, 1, 1, and that's it. Now, how well is our model performing? How well is our model performing? So let's see. So we'll need to, from sklearn.metrics, so we need to import accuracy score. So here we'd say our accuracy is equal to accuracy score, print and test Y. Print accuracy. So we have 94.7% accuracy, which is pretty high, although by the standard of these data sets, it's not so high. With some processing, we can achieve something better, but let's stop here for now. I've taken much of your time today. I hope you'll forgive me. And let's still take 1 or 2 questions before we close for today. Any questions? Any questions? You can take me back. It could be one of the things we've discussed before now. You can ask, and if you still face questions after the class, you can always go to the classroom and post your questions there, and it will be responded to. All right, so let's try to practice this. I'm going to send out this week's assignment hopefully by tomorrow, and it will be due in a week's time. And like I said, it's going to be based on the last part we discussed here, making or creating models or building models, basically. So that's what will need to be done. So in the absence of questions, I will say thank you for having me today. Thank you for your patience throughout the course delivery, and do have a wonderful evening. Okay, so somebody asked whether the updated notebook will be sent. So after every class delivery, I always update this notebook on GitHub. So every time, if you go to the GitHub, if you want to get the most latest notebook, so it's advisable to go to the GitHub page, the link that I usually share. So you can always get the updated copy there. So because after the class, I always update the copies there. I mean, the copy of the notebook there. All right, so I hope that answers your question. All right, do have a wonderful evening.
Thank you.